to do it if you're choosing a large group chosen, or a small group chosen from a larger group. As far as method, you're going to write down, oh, I do that by using the NPR notation. That's two methods. Okay. I love number 3. Number 3 is one of my favorites. What if some of your objects look exactly alike? Case in point, our favorite state to learn to spell when we're in elementary school. Who doesn't love spelling Mississippi? How much fun is that? Okay, but the question here is not how do you spell it, but how many different ways can you arrange the letters in the word Mississippi? A ton. Yep. But here's the wrinkle. Normally we would just go, well, there's 11 letters in Mississippi. I should just do 11 factorial, shouldn't I? But if I switch these first two S's, if I switch their position, does it make a different pattern? No. If I switch two I's into different positions, it's still the same pattern. So because some of the letters look alike, that doesn't make a different pattern. Therefore, should I get a larger answer or a smaller answer? Smaller. It should be smaller than the 11 factorial. What actually happens is you take the total amount you have and you do that factorial, but then you divide, because it's going to reduce how many you have because the letters are alike, you divide by how many are alike. And if there are several things that are alike, you divide by those factorials each time. So like in this case, Mississippi's 11 letters. What do you see that's alike?
4
Okay, so there's 4 S's. You would divide by 4 factorial for the S's. Okay, but you also said there were 4 I's, so you would divide by another 4 factorial because of the I's. And there are 2 P's that look alike, so you would also divide by that. So you would that's going to then reduce your answer. It's still really quite large. It's 34,650 ways. So anybody who wants to be a pain, I will assign you to come in and write me the 34,650 different permutations of the word Mississippi.
I want 100. No, you wouldn't.
I'd have you for the rest of the year. The worst problem would be figuring out what pattern have I used or not used. You'd have to have a very structured method for trying to do this, to keep track of where you are. And you would still mess it up. You're probably right.
Yeah, we're good.
It's not that hard to program a computer to do something like that. But
when I get home, I guess I'll get into that by myself.
I'd much rather you did your homework.
Okay, after I do.
Okay, so that's a like type problem. Okay, now it doesn't have to just be like what are the letters in the word Mississippi, how many ways can I arrange them in a pattern. A second example of how you could do this is, suppose you have 5 brand new identical basketballs. Six new identical volleyballs. And 3 new identical soccer balls.
Are they identical?
Okay, you're going to take and arrange all these balls in a straight line. How many ways can you arrange all these balls in a straight line? Alright, so what do is it just, okay, I got 14 different kinds of, so I just do 14 factorial and that's it? 14 factorial. Okay, because anytime they start saying the word identical, look-alike, indistinguishable, I love that one. If they're indistinguishable, you can't tell them apart. That means they look alike. Anything that implies that they look alike, you should be going, oh, it's a Mississippi problem. So I should divide by what? 5 factorial, 6 factorial, and 3 factorial. And you know what? I just changed the number here so I don't know the answer. Close. I would have to divide by another 30. 924, I think, but I'm not positive. Somebody might want to run that in the calculator. I just tried to do that in my head.
924 times 30.
No, because the one that I had 5 4 3, so I would need to divide by a 5 and a 6, which would be divided by a 30. So if I take my answer and divide it by 30, that should be it. But somebody have to run it in the calculator for sure.
So you want your new answer times by 30.
Okay, you would have to know my old answer. I just want somebody to put that in the calculator. 168, 168. What? No way. Oh shoot, there's 14. I had 12. Whoops, sorry. That's why. Okay. Sorry, forgot I had a different number on top. Did you say 968? Okay. 168,168. That's kind of cool. That's kind of a cool answer. That was kind of nifty. All right. So there you go. Way for coaches to torture you. Put those balls in all the different patterns out on the gym floor. And you have to do it running or something. I could suggest Mr. Thomas ways to torture students.
Yeah. Already. 924 is what we got. Anyway, it's just like Rachel, how do you get to school with that?
Okay, what I call specific locations, actually I should say specific locations or repeated objects. Okay. So this one I can give you several different ways. We're going to use those of you in this room right here, right now. And I have 7 chairs on the front row. And I know you all fight every day for the chairs on the front row. Or maybe because you've been a pain, I decide to assign you seats. How about that one? And I have decided I want sophomores on each end. I want 2 juniors in those slots, and the other 3 seats can be anybody. Okay? So I'm telling you, you have to have certain people in certain positions. That's what I call specific locations. Certain person in a certain spot. So when you do that situation, can I use factorial here? Can I just go, oh, it's going to be, 5, 10, 14 of you today? So is it just 14 factorial? No. I can't do that. No. You actually, the only way to do this kind where they tell you you have to have certain things in certain spots is to draw out the little blanks and fill in the number of choices in each spot. So drawing blanks is the only way to work these kind of a problem. Okay, do the ones that are dictated to you first. So, okay, sophomores. How many sophomores are in this room?
9.
9. Jumped on that one. Okay. So when I put the first person in a spot, there's 9 sophomores. I'm only counting the people in the room right now. Okay, so now, do the other sophomore spot. How many would there be to choose for that spot? There would only be 8 left. Okay, so then, now do the juniors. How many juniors are in the room? 4. So, therefore...
Not our fault, we're idiots.
No one ever but you said that. So there'd be
Change the.
Dave's over there agreeing like, yeah, we know.
4 juniors, okay, so then how many for the next? 3. Okay. Then here's the trick. What numbers for the other spots? It could be anybody that's left.
Just go answer it.
You guys,
Yeah.
yeah, exactly. There's 14 people in the room. We've used 4 of them. So then there's only left, there'd be 10 people left, then 9, then 8. Okay, then what would you do with all those numbers? You would multiply all those together. And factorial is not going to work on this one, because that's a pretty rounded set of numbers. 93, 3240. What'd you say? 622? Even? 80. Okay. So 622,080 ways to arrange people in the front row. Every day? No, we would have, how many would we have to do per day would be unbelievable to make it. Okay, so that's an example of specific locations.
But what are the chances of getting?
Let me give you a second example. This would be an example more of repeated objects. Okay, Kansas license plates are, what do they look like, the numbers?
3 letters and 3 numbers.
There's 3 letters followed by 3 numbers. Okay, so my question to you is, how many possible license plates can be made in Kansas?
A lot.
Okay, so letters, how many letters are there to pick from? There are 26. Okay, when I go to the next spot, can you repeat a letter on a license plate? Yes, you can. So therefore, since you can repeat, isn't there still 26 every time? So yeah, if things can be repeated, that's why you have to do the blanks again. It's not a factorial because it's not going down one number every time. And then, yeah, how many single-digit numbers are there? 10. There's 1 through 9 and 0. There are 10 single-digit numbers, so you'd have to times by 10, 10, 10, and you would times all of those together then. So if it's repeated, you just simply fill it in and work it out. That means in Kansas there are 15,600,000 different license plates that can be made.
How many numbers are there on the Social Security number?
The Social Security number has 9 digits.
10 times 4. 10 to the 9th power.
Yeah, 10 to the 9th power. A 1 and 9 zeros, or 10 zeros. No, 9 zeros to the 9th power, yeah. So it'd be 1 billion? Yeah. No, 1 million. But they also code those,
With letters too, don't they?
and well, and they have different regions. Like if you notice, Kansas, if you're born in the, it depends on where you're born. Like our numbers tend to run from like 507 to 515, 16. There's a certain, your first 3 digits of your Social Security number tend to also kind of indicate where you were born or where you lived when you applied for your Social Security card. Yeah.
Josh didn't get that answer.
You didn't get that answer? Oh, well, that's because I changed the problem. You're right. Oops, sorry. Sorry. Evidently last year I did it with I couldn't repeat a letter. This time I repeated the letter. Sorry. What did we get? I didn't pay attention to my own problem. Because I'd done a different problem last year and I don't have the right thing.
1, 7, 5, 7, 6, and then 3 zeros.
Okay. So 17,576,000. We got more that way. All right. So those are all ways to do linear permutations. You also have some problems today that want you to do circular permutations. Okay. Circulars, there's more limits on it. It's not as complicated as this. So how do we do circulars? And I have to kind of prove a couple points to you here. Do you think there would be more ways or less ways? If I have 4 objects in a line compared to 4 objects in a circle, is there going to be the same number of ways to arrange them? If I lay out 4 objects in a line and ask you how many patterns, or I put 4 objects around a circle, will there be the same number of patterns possible? Okay. Yes, I will tell you. No, I'm going to leave you a mystery and not tell you. I should stop though. Hold on a second.